Okay, so now that we are done with fluid statics, we'll be now moving into fluid kinematics. So essentially, the dynamic parts of fluid motion and how related forces uh, to a fluid that is moving. Right. So first we'll lay out this whole section. We'll be laying out the fundamentals of fluid kinematics. Uh, so starting off, we'll be first describing the Lagrangian and Eulerian descriptions and introducing you to concept of material derivative. Right. So when it comes to describing a motion, right, you can describe it in two different ways or two different perspectives. So be mindful when I'm saying it's different perspectives, right? So the motion is the same, it's just viewing it from different point of views, right? You can think of it the same, right? So depending on if you view from one point of observe it from one point of view versus the other, you'll see it slightly differently or might interpret it slightly differently, but the final result or the final physics or the final motion is the same, right? So you have to then connect those two interpretations. Okay, so one of these descriptions or perspectives or point of view is called as the Lagrangian description. Okay, so the Lagrangian description itself is what you're more familiar with, right? When you're doing solid mechanics, when you're talking about a solid deforming by either stretching or by contraction, by compression, right? You are technically following every particle as it deforms, right? Because how the lattice structure and the atoms are bound to its lattice sites, right? It vibrates about its lattice sites, right? So in solid mechanics, you're often looking or observing each particle as it deforms, right? But it's convenient in when you do that for solid mechanics because of how the lattice structures are confined to its lattice sites. And another way of describing objects is called as the Eulerian description, which is more commonly used in fluids where you don't necessarily follow each particle point by point. Right? You observe the deformations or the changes at a given location, and depending on the location that you're doing, you might have a new particle coming in or moving out because you're just observing at the same point, right? Okay, so naturally this is harder concepts, and this is where the challenges start for students, right? So, and that's I'm trying to give you examples and show you a couple of videos of trying to explain this and drive this home. Okay, so this video here shows a flow of a fluid around a circular cylinder, right? This is a method called particle image velocimetry, where they put a small dies of particles on the flow, and they are small enough that they are suspended in the flow and move around it, and then you shine a laser light and you can see those particles moving, right? So it is very obvious here of how the fluid is moving, how it's deforming, going around this, and you can see this region behind it where there's close to zero or no motion at all, right? So this would be an example of a Lagrangian description, right? Now that the fluid stopped, the motion stopped, you can see that there was a stationary, the particles also stopped as well, right? So here, this would be a form of or an example of Lagrangian description where each particle in some sense is following or following the flow itself, so following the atoms in the fluid, right? But then in order to observe or study things in Lagrangian description, you should keep a track of each and every particle and monitor it as it moves with time, right? So this often is not a very convenient mode of observing fluid, right? You can still do it, and people do it as this methodology uses, but it's always not the most convenient way to describe a fluid flow. Okay, and I think that this whole section will try to emphasize why one is preferred over the other, right? Okay, so another example which is using the same technique is that of a flow in a piston inside an engine cylinder, right? So often, right, you can kind of see the same thing as the valve opens and the piston goes down. You can see the fluid motion, and as it goes back, it's stationary, and then it goes back, right? So naturally, this is a very slowed down video of it. Okay. So the reason Lagrangian description is not convenient, I guess I can break it down into three possible reasons, right? Okay. So three reasons why Lagrangian description is not convenient, right? It's not that you can't do it. You can use Lagrangian description. It's just the fact that it is not often the most convenient means to observe. So depending on certain problems, people actually use Lagrangian description to observe fluid or to model fluid. Okay, so three reasons why it's not convenient for fluid problems, right? The first, and hopefully you will keep the two examples that I showed in mind of the videos, essentially of a flow through a cylinder and a flow into a piston, essentially, or inside an engine cylinder. Okay, so when you're doing experiments, right, think about when you're actually practically doing experiments. If you have to measure every particles, right, in this specific video that we show, the particles has to be light enough that it suspends in air or fluid, right, without actually disturbing the flow itself. So think about if you want to do pressure measurements or temperature measurements or some kind of other flow measurements, right? If you have to use an instrument to measure it, it won't be the most easiest way to do it of finding an instrument that is going to be so light and so small that it can suspend in air and move along with the air, right? Right. So that is kind of one of the reasons you can think about it. It's that for experimental measurements, for experiments or experimental measurements, right, it is not often convenient to put or develop a sensor that is so light enough, right? Or what do you usually see? You see that you insert a pressure gauge or insert a velocimeter into the flow, and you're measuring it at a single point in the flow, right? So you're not necessarily tracking or moving with the particle, right? So it's more convenient for experiment. It is convenient to put an instrument at a given location, right? And then just observe the variations with time, right? So you have to think about this is given location from space, right? So it's not the fluid can come in and out or move around, right, as it deems fit, right? So you're not necessarily tracking, it's more necessarily tracking the fluid particles anymore, right? So for instance, with the example of the flow around the cylinder, right, you had this and then there was a fluid moving around the cylinder, right? So if I have to measure, let's say, the pressure at this point or the velocity at this point, it's more convenient to stick a sensor at this location and just measure the fluid or the variations of pressure or flow around that point, rather than actually developing a sensor or that can flow around along with the fluid itself, right? Okay, so that's one of the reasons. Okay, the next reason that you can think of why Lagrangian description is not convenient is you are often concerned with how the fluid interacts with the object. Okay, you are not really concerned with what happens to the particle, let's say 100 meters downstream or 100 meters upstream of the desired object, right? So instance, if I go back to this example, right, you're often, if you're talking about a flow around a cylinder, right, let's say if you're doing an aerodynamics problem, right, computing how much drag is there, right, on this object because of a fluid flow, right? So you're concerned with how the fluid behaves around this region of the cylinder, right? You're technically not concerned with what happens to the fluid out here or what happens to the fluid way downstream, right? Okay, so your region of concern kind of gets limited to where the cylinder is, right? So if you, let's say, if you wanted to find the drag, you could have put like pressure sensors on the cylinder itself, right, and measure the pressure there or friction there, right? But in that case, you see it is stuck to the sensors are stuck to the cylinder, so it is at a fixed location and is not moving with the fluid, right? Okay, so this again kind of goes to the point that because you're often concerned with measuring the flow or measuring the flow characteristic of how the fluid is interacting with an object, it is more convenient in times to use the Eulerian description where you're not worrying about tracking the fluid particle or moving with the fluid itself, right, or tracking each atom. Okay. Lastly, and I think so this will be better explained further down the line, is that the fluid is constantly deforming. Just the definition of a fluid is the root cause of all the problem, right? A fluid is constantly deforming, right? So it's always changing shape over time, so it makes it harder to track. Okay, and this will be more better explained when I give examples of a Reynolds transfer theorem later in this section. Okay, so I'll keep that there, right? So as a result, it is more convenient to use Eulerian description where you're not constantly moving with the fluid particle, rather you're just observing a specific window and observing any deformations in that or changes in that specific window, right? So as a result, Lagrangian description is preferred when you're observing or studying solid mechanics and Eulerian description is preferred for fluid problems. Okay, and notice that I've used the word preferred, right? That means you can still use an Eulerian description or Lagrangian description for fluid problems, right? It's just not most the convenient way. So most of the time, whatever you will see, all the equations will be in Eulerian form, right? And this kind of forms the root cause, I feel personally, for some of the students. Because so far you have been learning everything from the solid mechanics perspective. So you have been looking at everything from the Lagrangian point of description. Okay, so now it is a kind of big switch. It's like you're used to doing something one way for so many years. Now you have to try to look at it slightly differently. So it becomes a kind of a big switch for students to kind of observe things in an Eulerian from the Eulerian perspective, right? So that switch is sometimes becomes challenging for students. Okay, so to better explain this, I will use an example here. So let's say there's a river, right? And there's a factory on one of its banks, right? And the factory is dumping out pollutants, right? So if this river is flowing, right, whatever the pollutant is being dumped out, it will get, let me use a different color, right? So whatever the pollutant is getting dumped out, it is getting dragged, or it goes downstream or flows with the river itself, right, with the flowing river. Okay, so if you're tasked with, or if you want to observe the concentration of the pollutant, or how much the pollutant is being dumped from this factory, there are two different ways you can do this, right? One is you can place a sensor. You can be a person, or you're a person sitting on the side of the river bank and place a sensor here, and probably you have a rod connecting it, right? And that sensor measures the concentration, right? Okay, so you're measuring the concentration okay, with respect to time, okay? But in this case, your location is fixed. So let's say initially you had, if you are measuring at this point, right, and the pollutant have already been started to dump, right? So by the time you started measuring, there was already some pollutants there, and it has been polluting at a constant rate. So you can see a constant value or concentration of the pollutant. Let's say the factory starts dumping more pollutants, so you'll see a spike in the concentration. And let's say if you start reducing it, then you'll see it back going down, right? So at that specific location, you can measure how the concentration of the pollutant changes with time. Okay, right? So that was one way of looking at this, right? Or one way of observing the concentration. An alternative way is, let's say if you are in a boat, right? It's not a motorized boat, it's just a boat that is floating in the river with the current, right? And now you have a person. I'll draw a stick figure, do my best. And then this person has a probe and he's inserting the probe into the water, right? But since it's a boat that is floating, is moving with the current, right? So if you're measuring the data of concentration with time of this person who is on the boat, right? One of the biggest changes is that fact that since he's moving with the river, his location is not fixed. Right? So since the location is not fixed, you are constantly changing location and as the river moves along, right? So let's say if he started off upstream, right? Here if he's trying to measure the concentration of the pollutant, he's going to get none because he's upstream of the where the plume is or pollutant is being dumped, or upstream of the plume, right? Now it's going to be 0 till he gets to this point, right? As soon as he starts entering into the plume, he'll see a spike in concentration and it will stay steady for the most time part, right? So as he moves along, it will stay steady till he gets out of this plume area and then it will start dipping back, right? Okay, so both of these people are measuring the same pollutant concentration, but they're measuring it slightly differently, right? So this is the main difference in some sense between the two perspectives, right? So this, where you are following the stream, this is similar to following the fluid particle, right? So this is analogous to the Lagrangian description, and this is more analogous to an Eulerian description, right? Okay, so one thing that you must understand is, let's say if this person is flowing and moving with the river, at some point he will come across the same point where this sensor is, right? So there will be one point in time and location when these two quantities will be exactly the same, or measuring or observing, or let's say outputting the same exact value, right? Okay, so as a result, right, the takeaway should be, right, you're measuring the same quantity or observing this, trying to observe the same physics or dynamics, but you're using different perspectives to look at it. It's like different point of frame of reference, right? It's like probably you heard of a moving frame of reference versus a stationary frame of reference, right? You can think of this as being an analogy to that, right? So since Eulerian description is from a fixed location, you can see this is something that will be becoming more intuitive to you if you wanted to measure concentration, and this is something that you do, right, rather than sitting on a boat and tracking it, right? Because like we said, like you are not really concerned with what is happening at this point, right? Okay, because this is upstream, right? You're most concerned with the concentration changes occurring in this region where the plume is actually, right? So as a result, it's generally in fluids you use or prefer the Eulerian description over the Lagrangian description, and it's not that you can't do Lagrangian description, right? So hopefully this example helps you understand this kind of difference between Lagrangian and Eulerian description, and why one is preferred for solid mechanics, which is the Lagrangian description, and one which is Eulerian description is preferred for fluid mechanics, right? Now our next goal will be trying to connect these two, right? So trying or deriving a relationship that will connect allows us to go back and forth between Lagrangian and Eulerian description. So it's kind of like a transformation, right? Like you do coordinate transformation. In that sense, it is like allowing you to go from a relationship we are trying to derive that will allow you to go from a Lagrangian description to an Eulerian description. Okay, so now that we have some understanding of the Lagrangian and Eulerian description, our goal here is to connect these two forms of description, or essentially find relationship to connect these two. The first relationship that we'll be deriving will be for the differential form of analysis, or differential analysis. Okay, so in this one, we first start off by drawing a coordinate system. So let's say we pick a coordinate system, a two-dimensional coordinate system, x and y. Okay. And essentially we'll be tracking fluid particles in this domain, right? So in order to track a fluid particle, let's say we used some kind of ink or dye and marked this set of fluid particles, right? So be mindful when you're talking a fluid particle, right? It still has a bunch of atoms in it. It's like talking about a dust particle, right? For instance, a dust particle is light and will flow around with the flow of fluid or airflow, right? But that does not mean a dust particle has just a single atom, right? It has a lot of atoms in it, right? Similarly, you can think of a fluid particle. It's very tiny in size and shape, but it still has a collection of fluid atoms in it, right? So make a distinction on that, right? So we put a dye and to designate a fluid particle in this domain, and the initial position vector for this is given as A, which is a function of x and y, and the time here is t is equal to 0. Okay, now after a certain time, if there is a flow in this fluid, let's say there's a flow like this, right? The streamlines kind of go this way. Okay, so this fluid particle will flow along the streamline, right? So after, let's say, a time delta t, this fluid particle would have reached a new location, but since you can see the streamlines have stretched and expanded, it will be at a new location, and that will kind of deform as it moves along, right? So now this same set of fluid particles have deformed in state. It might have stretched a bit and moved along, right? So this location of the fluid particle at any given time is provided by this vector r, right? And this is a function of the specific fluid particle that we started at. So this specific fluid particle that we started at, or put a dye on at t is equal to 0, right? So we are tracking that fluid particle, right? So it's a function of this initial position vector A, and then a function of time. So if at later time it might move around, right? Okay, so now that we have defined the position vector for this fluid particle, let's say if we are concerned with looking at the concentration of a certain quantity in that fluid, which is designated by this fluid particle, as it moves along with respect to time. So essentially we are trying to track concentration, right? So concentration is function of the position vector and time, right? But we just saw the position vector itself is a function of the initial position and time. Okay. So now if we are concerned with calculating the rate of change of concentration with time, right? So in a differential sense, how do you find the rate of change of concentration? So our goal is to find the rate of change of concentration, right? So essentially we want to find the rate of change of concentration. In a differential sense, you write d by dt, which is time derivative of a quantity or the change of a quantity with respect to time for a given position, where for a given position vector or initial position vector. So that is a is constant for you, and we are concerned with the variable of concentration. So essentially this is a time derivative of concentration, right? This concentration is a function, as we already mentioned, of the position vector, which in turn is a function of initial position time and time, right? So if we want to find this time derivative, right, how do we go about finding it, right? Because it's a function of multi-variables here. Essentially, in order to find this derivative, if you remember from calculus, we use the chain rule, right? Okay, because the problem is the concentration is a function of time, right? But this location is also a function of time, right? So if you end up using the chain rule, you get something like this, right? First, you take the time derivative of the concentration with respect to time, so you get just concentration or change in concentration with time. But now you want to take the time derivative with respect to r, right? But r itself is a function of time, so you break it up. So essentially you get d concentration over dr and dr over dt. Okay, so remember that r is a position vector, right? So r is a function, or it relates to, if you look at it in component form, has x and y and z coordinates, right? So what does this term represent? Right, a position vector with respect to time, or location with respect to time, or let's say distance divided by time. What is this variable called? A distance with respect to time. This distance with respect to time, or distance divided by time, or location divided by time, is nothing but the velocity. So this quantity essentially represents the velocity vector. That means velocity component it includes the velocity component in x, in y, and in z direction, right? These are the standard terminology used of u, v, w for velocity component x, y, and z direction. Okay, so essentially this expression can be expanded. For your understanding, I'll expand it and write. So this is essentially saying as this is the same expression, right? So this is essentially saying as d concentration by dt plus d concentration by, sorry, let me just, d concentration by dx times dx dt plus d concentration dy times dy dt plus d concentration dz dt, right? So because we are considering a three-dimensional, if we consider to generalize a three-dimensional object, right? So this operation, there's a shorthand for that, and it is, so for, there is shorthand for this, which is essentially called as the gradient operator, or the divergence in this case. So velocity vector dot this gradient operator times c, right? So this gradient operator means nothing but the derivatives in x, y, and z. Okay, this is, there's a further shorthand for this whole relationship called as capital D over dt, and your operator is acting on the concentration, right? So this expression is called as the material derivative. Okay, so what we have derived is an operator that can act on a variable that will help it connect or convert from Lagrangian quantity or variable to an Eulerian quantity or variable, right? What I want you to focus on is not necessarily on the derivation itself. Derivation is something to be handy to know where it's coming from, but focus on each term and how it helps connect these two frames, right? And that's what we are going to go over with the help of a couple of examples in the next few slides. So again, so first off, this material derivative is an operator, it's a mathematical operator. It can act on different variables, right? So we chose concentration partly because it's a scalar quantity. You can have this variable to be pressure, it can be velocity, it can be, let's say, density, right? We already talked about concentration, right? So it's a mathematical operator that we derived which can act on any of these variables, right? Or let's say stress, right? Depending on the variable you're choosing, you can use this operator, right? So this operator is essentially helping you connect Lagrangian description or convert Lagrangian description to the Eulerian description and vice versa, right? And this operator is used, naturally it's a differential operator, so it's essentially used for differential analysis. Okay, so again, so this operator, if you want to expand this operator again so that you clearly remember or see, you have ddt of this concentration term, right, is equal to partial time rate of change of concentration plus Vx, or let's say u, because we just mentioned how u is just the velocity component in x direction. So you have u dz dx plus v dz dy plus the velocity component in the z direction w times dz dz. Right, so uvw is, if you have a velocity vector capital V, small u, small v and small w is just the x, y and z velocity components in those three directions. Right, so essentially consider that you have a velocity vector. This is u, v, and the z component is w. Right, hopefully that is clear. Right, so what you have on this left hand side is represents the Lagrangian description, or the time rate of change of concentration from the Lagrangian perspective, and what you have on the right hand side is the change of concentration if you look at it from the Eulerian perspective. Okay, so now in order to better explain this, let me give you an example. Right, so let's say, hopefully people have been on a roller coaster or know about a roller coaster, right? So let's say if you are on a roller coaster and you're slowly climbing up for the first fall of the roller coaster, right? So you have a car, you're seated on inside one of the trolleys or a car that is on this roller coaster, right? Okay, so as you go to the top and you start falling down, right, you can feel the acceleration, right? You can feel the change in velocity, right? Okay, as you're speeding up and going down, right? You can naturally, if you're falling down in a roller coaster, you are getting pulled by the gravitational acceleration, so your velocity increases, right? So if now you want to find the time rate of change of velocity with respect to time, right? So you're trying to find the velocity vector, right? So if you're a person seated in the car, right, you're moving with the car, right, or with the roller coaster, right? So you are, in that sense, if you're measuring or feeling the velocity, you're measuring it as if you were Lagrangian frame of reference, or as if you were a person sitting in the fluid particle, right? Okay, now if so, naturally feel some kind of acceleration, let's say a, right, because the velocity is changing with time and you can experience it. Now if you're looking at the same roller coaster, but now your friend is sitting outside. He's not on the roller coaster, he's sitting on a bench outside and he's observing this roller coaster as it moves along, right? And you are still in the roller coaster, let's say, right? But somehow his view is blocked by, let's say, there are buildings or some kind of tower, so he can only see a small window or a small section of a roller coaster, right? So okay, so this will be something in similar to the Eulerian perspective, right? So you are not sitting in the roller coaster, or you're not following the fluid particle, but you're a person or observer from outside looking in. So you as an observer are not moving, you're stationary with respect to the fluid particle, right? So connect this to also the example we gave of a plume of water, a pollutant plume in river flowing, right? So now if you're in the Eulerian perspective and you start trying to compute these terms, right, the first term talks about dv dt, right, change in velocity with respect to time, right? So if this person who is sitting outside, so he is in the Eulerian perspective, right? So for this person who is sitting outside, will this velocity be changing with time if he's just looking at the same position every single time, right? So let's say if this cart passed by at t is equal to 0, right, it had certain velocity corresponding to this location, right? And at a later time, let's say t is equal to 10 seconds later, there's another cart that comes and takes up this position. Naturally, at this position, its velocity will be same as the previous cart was, right? So if it's looking at the same location, right, essentially dv dt is nothing but change in velocity with change in time, right? So if he's looking at the same position, he's looking at different carts that are at the same location at different times, right? But if he's just looking at the roller coaster of the change in velocity, right, the velocity at this position of different carts of the roller coaster will be the same at different times, right? So for him, there is no change in velocity with respect to time for this observer who is outside, right? So for him, this quantity is going to be 0. Okay. Now what about this quantity that is corresponding to u, let's say du dx, right? Okay, so if you look at the velocity of this, we definitely know there is some velocity he can observe of this cart, of this roller coaster. So u is not equal to 0, right? And what about the spatial acceleration? Is the velocity changing with location, right? Naturally it is accelerating, so the velocity here in this location is going to be different from the velocity. So the velocity in this location will be different from the velocity in this location, and it will be different in this velocity, right? So you will have a velocity gradient at this point as a result of it. So this term is not equal to 0, right? So now you can see how these two relate, right? So your material derivative, if I'll just, so that I use the same slide and you can see the same things, right? So if I'm wanting to find the material derivative to connect the two, right, you can see dv dt was the Lagrangian frame of reference, right, and you got some acceleration a, right? In the Eulerian frame of reference, dou v dou t was 0, but the spatial acceleration was not 0, right? So this du dx, u du dx, right, was not equal to 0, and what you'll end up finding that this will be equal to a, right? Okay, so then regardless, and this was the Eulerian frame of reference, right? So essentially this operator helps you connect these two frame of reference. If you're either a person sitting in the roller coaster or you're a person observing from outside at a specific location, you end up getting the same quantity or the same variable or same changes using this operator, right? Okay, so that's essentially what the goal of this operator is. So another common example is that of something that we previously mentioned when we did unsteady and unsteady flow. Is that of a hose with a nozzle, right? Let's say we have a hose of constant diameter and there's a nozzle connected to it, and we have a uniform flow, so the velocity is constant. At point 1, it will be the same velocity at 2, and we talked about how the cross-sectional area is decreasing, so the velocity will increase at 3, right? So you have v3, v1, you have certain velocity at v2, which is going to be same as v1, right? So if we are trying to draw the velocity vector, right, or plot velocity with location, you'll see the velocity corresponding to point 1 is going to, if that is v1, v1 and v2 are the same, so you have a flat line, and then you start accelerating, so you have an increase in velocity v3, right? So what these two terminologies, so again if you go back to this material derivative, right? Sorry, right, so this time derivative in the Lagrangian sense is equal to, can be rewritten as the material derivative. So if you want to do again for the velocity, right, which in turn can be expanded out, right? So this material derivative can be expanded out, right? This is just an operator, okay, and it's a shorthand for writing this full expression. So let's say we are just talking about the velocity vector and in a single component, because we are doing a 1D problem to make our life simpler. So this essentially expansion goes to dv dt or dou v dot t, and then v times dv dx, right? So this first term, it represents the time rate of change of velocity, okay, while the second term represents, okay, so let me just write it down so it's clear. Okay, and this is from the Eulerian perspective. And the second term represents the acceleration or spatial acceleration, or in this term with this velocity associated with it. So it represents the flux, or is also called as the convective acceleration. Okay, and this is also from the Eulerian perspective, right? So spatially, if your quantity is accelerating, okay, so in this problem, right, in this specific example, and there's a main reason to highlight this, right, is the velocity at a given location changing with time? So is this dv dt, is there a time rate of change of velocity in this problem? Is the velocity changing with respect to time? Okay, so we kind of alluded to in the previous sections, but here most students end up saying that it is changing with respect to time, right? So it is an unsteady problem, but they're mixing up the changing of because of this change in velocity right here, right? So the issue is there is a velocity change here, but this velocity change is a spatial change in velocity, right? It is not a change in velocity with respect to time, right? So essentially, if I measure the velocity at this outlet at certain time is equal to 0, and then after a minute came back and measured, it will still be the same velocity v3, right? So it's not changing with respect to time, it's changing with respect to space. So make that distinction here, right? When you're saying time rate of change of velocity, right, in our written description, it's for a given location. So for a given location, there is no change in velocity with time. So this term actually goes to 0, right? Now, when you look at this term, right, this is the non-zero term, right? Because this is talking about velocity changing with space, which is what it is, right? So dv dx is nothing but change in velocity with change in space, right? So keep that in mind, right? So, that make the distinction between velocity changing with space and velocity changing with respect to time. Okay. So as we talked previously, right, you just need to have a basic top level understanding of this material derivative, right? Essentially, material derivative is helping you connect Lagrangian description to Eulerian description, and this is given by this material derivative of this operator ddt, which is called as the material derivative. And this ddt is essentially a shorthand for this expression, or this complete expression is given as this, right? So depending on what variable you have, okay, but this quantity can be, it depends on whichever quantity or variable you're operating on, you can use this operator, right? So this can be velocity, we talked about concentration, it can be density, it can be pressure, it can be shear stress, okay, so on and so forth, right? This allows you to go back and forth or connect the Lagrangian description to the Eulerian description, right? So that's kind of the goal, and that's the big takeaway you want to take away from here, right? Okay. So these next few slides essentially talk about the topics that we just covered, or the context, the concepts we just covered, right? These are just directly from the notes, and it's going to be reiterative, right? So don't worry too much about the derivation. All we want you to know is the final expression and have an understanding of when you're using it, what you're using it for. Okay. So that kind of brings us to a close of this section, part of the section, right? What we'll be next looking at, so we looked at the differential operator to connect Lagrangian or Eulerian description, right? In this class, we'll not be using too much of a differential calculus, right? What we'll be looking at will be more on the integral sense, right? So cumulative forces, cumulative momentum, right? So essentially what we now need is a way to connect the Lagrangian and Eulerian description if we are doing an integral analysis rather than differential analysis. So that is what we'll be focusing on in the next section or part of this section itself. Okay, so now we'll move on to the second part of fluid kinematic fundamentals. So the two things we'll be primarily focusing on is kind of trying to describe the control volume concept and the Reynolds transport theorem, that is the relationship to connect the Lagrangian Eulerian description if you are doing an integral analysis. Okay. The concept of streamline, pathline, and streak line, types of fluid motion and deformation, those are something that we'll not be specifically covering, but something that you can look up, and is additional knowledge for you to gain if you're interested in that. Because types of fluid motion deformation is similar to deformations and motions that you have learned in solid mechanics, which is rotation, shear, linear strain, right? And streamline, pathline, streak line are a concept that you can, something that is an additional information for you to have an understanding of, which will not explicitly be going through, but something that you can read and from the notes or the textbook. Okay. So now here we are talking about doing an integral analysis, right? So the main difference between a differential analysis and an integral analysis, right, is when you're doing an integral analysis, right, you're looking at a cumulative force. You're looking at cumulative mass flux, right? You're not necessarily looking at the distribution, spatial distribution of forces, right? Because if you're doing a spatial distribution of forces, that is a differential form of analysis that you do, because you're looking at different points or point-wise distribution, right? If you're just concerned with the net force, net mass flux, net momentum, then we are looking at integral analysis, and that will be the main thing we'll be focusing on in this undergraduate fluids class, right? So it will be all integral form of analysis. Okay, so similar to or analogous to how you had the Lagrangian Eulerian description, right? There are two methods of analyzing a fluid problem in an integral analysis, right? The first and this is very similar, or it forms its basis on a closed system and an open system approach. Hopefully you guys are familiar and can recall what a closed system is. And an open system is, right? A closed system is one where there is no mass transfer or mass flux through the system or through the boundaries of the system, whereas an open system is one which allows for mass transfer and transfer through, or mass flux through, the boundaries of the system that you're looking at, right? So these kind of form the basis of what we are going to do next. So the closed system is also called as the systems approach, which is similar to this example here, right? So closed system, and that is same as the systems approach that we are looking at. This is analogous to the Lagrangian description. Okay, so if it's a closed system, right, and if you're talking, and the best way to explain is using this example, if you're talking about looking at all the contents of fluid or spray contents inside this deodorant, right? So you initially marked this container, right? Before it was sprayed, this container was holding all the spray contents, right? So the surface of the container forms the system that you're looking at, right? Because that is holding up all the mass of the spray. But now if you spray the deodorant, right, some of this mass is getting out. So in order to maintain a closed system approach, you will have to modify your boundary. Let me use a different color. You will have to modify the boundary of your system to kind of capture the spray that has left the container itself, right? So you're modifying the boundary of your system, or the volume that is contained in the system, so that it remains a closed system, right? So that the net mass, there's no net mass transferring the boundaries of the system, right? Okay, so you can see how this can be of an issue, or it can get cumbersome when you're looking at fluid problem, right? So if you spray this deodorant, is constantly diffusing and spreading, so you have to constantly keep on tracking all of the mass of the spray, and then constantly deform the system boundaries or the system volume to make sure that it is similar to a closed system, right? Okay, so that there is no net mass transfer across the system and the total mass remains the same, right? Okay, and so this becomes an inconvenient approach, right? What we then use, or what we more commonly use in for fluids problem, is this open system approach. It's this open system concept, right? So which is called as a control volume approach. Right, so this is control volume approach, and this is analogous to the Eulerian description, right? So essentially here, since this is an open system, you do not need to worry about making sure that there is no mass flux in the boundary, right? It's an open system, so you can have mass flux or mass leaving the boundary of the system. So if you spray out, that is fine. You don't need to deform the boundaries. All you need to account for is how much of the mass is leaving the system, right? If there's some amount of mass leaving, you just account for how much is leaving the system or entering the system, and that's it, right? So this becomes a more convenient approach for a fluid problem, right? And as a result, for fluid problem, we use this control volume approach, right? So similar to the material derivative, now the goal is how can we connect these two approaches, right? How can we connect these two approaches, right? For that, we use a relationship called as the Reynolds transport theorem, or RTT. So Reynolds transport theorem, right? So that's where the RTT abbreviation comes from. Okay, and something to kind of note on the side is this control volume notation that I've written. So in fluids, often volume is written as V with a line going across, right? This is just to make a distinction between, because in fluids you always also use velocity is a variable that is commonly occurring, and that is also v. If it's a velocity vector, or small v if it's the component of the velocity vector in the y direction, right? So in order to make a distinction between, if you're talking for volume or if you're talking about velocity, when it's volume, they always just cut or put a line across the v to make a distinction that you're talking about volume, and not mistake it to say mistake it and understand that you're talking about velocity, right? So in order to remove the confusion, they use that terminology. Just keep that in mind, right? So essentially here the goal is, right, to use Reynolds transport theorem to connect the system and control volume approach, right? And something you will see soon, part of the reason we are going through so much length to connect the system and control volume approach, or to connect the Lagrangian and Eulerian description, is because most of the conservation laws that you're familiar with and that you know about, right? Like the mass conservation, momentum conservation, Newton's second law, energy conservation law, right, are all kind of described or written for a Lagrangian form of description or a system form of description, right? So that's part of the reason, if you want the equivalent form of this conservation laws for a fluid system, which is more convenient to look at Eulerian form of description or control volume form of description, you need to convert these conservation laws into those descriptions. So you use this Reynolds transport theorem or material derivative concepts to make that conversion on the jump. Okay, so that's kind of the reason we are doing it. So if you have a good understanding of how the Reynolds transport theorem works, right, you can easily derive the mass conservation law, momentum conservation law, and energy conservation law by just literally substituting the variables. Okay, but first off, before doing this, we'll talk briefly about the control volume itself, right? Okay. Okay, so when it comes to control volume, right, there are three different types of control volume that you will be using in this course. So first is what is called as the fixed control volume, right? So essentially in this case, right, the name would suggest it, right? The control volume is not moving and not deforming. Right, so essentially, let's say if you're looking at you have a pipe or even a nozzle or a hose. Let's say if you're talking about a rigid pipe or a duct, if you're studying about flow through that pipe, right? In this case, right, if you are trying to study is your control volume or your system is going to encompass this pipe, so that's what you're concerned with, right? But since this is a rigid pipe, right, hence it is not going to be deforming, right? So the shape would not be changing. That's what it means by deforming, right? So if the control volume shape is not changing with time, right, then it is a not deforming control volume, right? Okay, and also since this is a pipe, it's not moving anywhere, let's say, or let's assume that it is a water pipe that connects a dam or a water reservoir to the water tank, right? So it's a rigid pipe which is not moving and is stationary and fixed to the or buried underground, right? So that is results in this pipe not moving, hence your control volume is also not moving, so it's stationary, and because it's rigid it's not deforming, right? So then this becomes an example of a fixed control volume. Okay, so just keep that bear in mind, right? So anytime you have a control volume or a problem that is given, right, so similar to a free body diagram, if you're given a problem in the consequence sections, when you're doing the schematic, I need to see the control volume that you draw, right? Because depending on the control volume you drew, you might be right or wrong in your answer that you do, right? And then making the identification that if it's what type of control volume is, right, that will help simplify your problem or the equations that you're using, right? So that's part of the reason of being good at identifying what type of control volume is, right? So the best way to get better at identifying it, right, is to actually practice it, right? So even if you're looking at example problems, homework problems, or textbook problems, or things that you found online, you don't need to solve the problem, but depending on the question that is being asked, depending on the factors that are given to you, right, and right, you can practice and see like, oh, which would work best? Is this a fixed control volume, right, or some other type of control volume, right? So in order to identify what type of control volume it is, you just need to ask yourself these two questions. Is the control volume, so right? When it comes to control volume, right? So first question is it moving, right? The second question is it deforming, right? So that will help you determine what kind of control volume, right? So now we just looked at, in the case of fixed control volume, it is not moving. So not moving, and it is not deforming because it's not changing shape, hence it's a fixed control volume, right? So hopefully that will hint you towards what is the next type of control volume, right? So the next type of control volume is a moving control volume, right? Okay, so let's say a good example would be if you're doing an aerodynamics problem of studying flow around a moving car, right? So this car is moving with certain velocity and you're looking at how the flow behaves or how the aerodynamic forces acts on this car, right? Okay, in this case, right, you're concerned with how this fluid is interacting with the car, so your control volume essentially encompasses the car itself because you're focused on interaction or the impact of the fluid on the car, right? So you're constantly tracking the car as it's moving around at different velocities, as it's moving around the track if it's a racing car, right? But since you're constantly tracking the car, right? So you're moving with the car, right? So if I go and ask you these two questions again, right? Is your control volume moving? Right? So your answer to that will be yes, right? So control volume is moving with the car, right? So the car is not stationary, you are parked, it's constantly moving, and your objective here is to study the forces on it as it's moving, right? And that's why the context or what is being asked matters, right? So if I would have asked, like, if the car is parked and you have a gust of wind and then you want to see the forces acting on the car, right? Then in that case, your control volume is fixed because the car is not moving, your control volume or your system is not moving, right? Okay, so make that distinction. So depending on what is being asked, it can be one or the other, right? Okay, so the second question that you needed to be asked is the control volume deforming, right? So since you're concerned with aerodynamic forces on the car, the control volume encompasses the car itself, right? So the question is the volume changing in shape or deforming in some form, right? Right. For it to change in shape, the car has to change in shape, right? But car is not deforming, right? Car is not changing in shape at all, right? So as a result, the answer for this is the control volume deforming? And the answer would be no, right? So for a moving control volume, right, essentially the control volume is moving with a certain velocity, the control volume is moving but not deforming. Okay, hopefully that is clear. Okay, so I guess you can guess what is the last control volume or type of control volume, and that is deforming control volume. So okay, so if you were given a problem of that of looking at monitoring the pressure or the contents of air contents or mixture contents inside an engine cylinder, right? So a working engine cylinder, so you have an engine cylinder that is there and you have a piston inside it that is moving up and down or going through the cycle of an engine. Okay, so and what you're concerned with is what's happening to the air inside it. Okay, that's what your concern is, right? So this volume is constantly increasing or decreasing, right? So this volume is either decreasing or increasing depending on the motion of the piston, right? So if the piston is going up, it is decreasing. If the piston is going down, it is increasing, right? So in this case, right, if we go back to the question of, right, so is the control volume deforming? Right, and the answer to this would be yes, right? The control volume is deforming because if you're constantly looking at the air or the mass of air or the pressure in that fluid trapped between or trapped in the engine cylinder through the cycle, right, through a 4-stroke or 2-stroke cycle, then your volume is changing, right? So hence your control volume is deforming, right? But what about the second question? Is it moving? Okay, you have to be mindful when we are saying moving, we are talking about the whole volume moving with certain velocity, right? So is there a certain velocity to the whole volume, right? And the answer to that is no, right? So make a distinction between just the boundaries moving, right? So this boundary here is going up and down, but that is deforming, but the whole volume in itself is not displaced or going anywhere, right? So hence it is not moving, right? So for a deforming control volume, essentially the control volume deforms but is stationary or not moving. Right, so these are the main 3 types of control volumes that are there, that for you need to get better at identifying, which will be required for subsequent sections that you'll be doing, right? So make sure you get a good grasp of this, otherwise the next 3 or 4 chapters you'll have some trouble with it, because you'll need to identify a control volume or what type of control volume you're doing for different problems that you'll be asked in exams and homeworks, right? And finally, you can think of a third class of the most general class of control volume, which is just a combination of moving and deforming control volume, right? In which case it is both moving, so it is moving with certain velocity, and deforming, right? So in that case you can think of a hot air balloon, right? So it is rising up in the atmosphere, but as it is doing so, the balloon's shape is also changing because the atmospheric pressure is changing as it increases altitude, right? So that is one form or one example you can think of moving and deforming control volume. Okay, so now that we have laid this foundation, or you're clear about just the basic control volume concept, next we'll be going through the derivation of the Reynolds transport theorem that will connect this control volume concept to a system. Okay, so in order to derive, right, we first define a variable b that is representative of any extensive property. Hopefully you guys remember about extensive and intensive properties, right? Extensive properties are properties that are dependent or change with a change in volume or change in mass, right? Means an extrinsic property is, examples of it is mass, energy, and momentum. And another variable is defined, which is small b, which is the equivalent intensive property, which is just capital B divided by small m, right? So you can convert an extensive property to an intensive property or find its equivalent by just dividing it by mass, right? So it gives you the corresponding intensive property, right? Okay, so we'll use this to define a general relationship, which is the Reynolds transport theorem, to connect the closed system an open system concept, or a system concept and a control volume concept, right? Okay. So here I will briefly go through the derivation of it, right, just to give you guys an understanding of it. But note, the derivation is good to have an understanding of, but it's not what we are focusing on, right? We'll go through derivation, but finally what you're concerned, or the main focus or takeaway, should be understanding the relationship that we'll be covering at the end of this, after this derivation, and understanding what each terms mean in that relationship for a Reynolds transport theorem. So in this relation, to go to a derivation, we are essentially using an example here of a converging nozzle. You can do it the other way around, of a diverging nozzle, right? So first we are looking at a system or a fluid volume, right? So there is a converging nozzle and you have flow through it, right? So it's entering on one side and is exiting on the other side with a different velocity, right? So in order to derive the Reynolds transport theorem, we first start with defining a system, right? So let's say in order to define a system, what we choose this section of the fluid as our system, or this volume of the fluid, right? So you can think of it as, let's say, because we want to make a comparison between closed and open system and Lagrangian or Eulerian descriptions, or the system and control volume approaches, right? So let's say we added some dye to that volume of fluid, right? Okay, so at time t is equal to 0, right? So at initial time t is equal to 0, right? Your system, or the whatever the property is occupied or concerned with by this volume, is going to be the same for a closed system and for an open system, or for a system approach and a control volume approach, right? Okay, right? So even though I'm going to explain it in terms of provide the description in terms of B, you can just think of as the physical volume, as a geometrical problem, right? Now at a later time, let's say t is equal to t1, right? Since there's a flow, right, this volume or this fluid that has been marked by this would have moved to a new location, right? That is what is given by this green sketch here, right? So it has moved to a new location. Okay, and this is the case with trying to capture it from a system or closed system or point of view, right? Because you cannot have mass transfer, you have to move with the fluid, right? But in the case of a system or control volume approach, you are still looking at this volume itself, right? You're not moving with the fluid. Okay, so for a control volume, you're still your volume that you're concerned with is this related to the red one, right? Okay, so at time t is equal to t1, you are not looking at the exact same volumes, right? Okay, so if we want to write what is this volume that is in green at times t is equal to t1 in relation to this control volume that is going to be still the red one, right? Because the control volume is not moving anywhere, your system is not moving, right? Or does not need to move, right? You can do that, right? So if you just are looking for a geometric perspective, right? If let's say if you want to, all you want to do is worry about this volume, or rewrite or get an expression for this volume that is green from things that you know, right? So essentially if you knew the initial control volume, that is the red part of it, right? So if you subtract this volume that is given by 1, so if you subtract this volume from red that is given by this expression right here, and then add this 2 volume that is new there, right? So it's added to that. Okay, so if you, let's say if you end up adding this volume to this initial control volume that was there, what you end up getting is this green volume that you're looking for, right? Okay, so that's kind of the first step here, right? Okay, so this essentially becomes equivalent to the system, right? Because the green volume is the description of this property or volume of the system, right? Because you're tracking and moving along with the same fluid particles, right? So this is equivalent to the system volume, right? Or whatever the property, extensive property you're looking for the system, right? So now if you want to find the time rate of change of this property or volume of the system, okay, you have this expression for time t plus delta t of how much this quantity is for system, and you have this expression of how much how much this quantity or extensive property was for a system at time t or equal to 0 or initial time, right? So if you want to find the time rate of change of that quantity, all you need to do is subtract these two quantities at t plus delta t and times initial time divided by delta t, so to find the change, right? So over a certain time, how much of it changed or how quickly it changed, right? So if you do this to the relationships that to the equations that you got above, you will get these relations out here, right? So if you plug in the values or relations from the previous slide to this, you'll get this expression. Okay, now if you remember, if you want to find a derivative, is just a limit of delta t going to 0, right? So if you want to find a differential relationship, right, what you end up doing here, right, is taking the delta t going to 0, so you get that the time rate of change of B as a system is equal to the time rate of change of B as a control volume minus the amount or rate of this amount of quantity of B entering that control volume plus the amount or rate of B leaving the control volume, right? So if you want to further go ahead and write B instead of an extensive property but the equivalent intensive property, right? We will remember small b is nothing but capital B by M. So in other words, small b is equal to, capital B is equal to small b times M, right? And M is nothing but mass, so it's density times volume. Okay, but here you are not concerned with just B, but B dot, which is the time rate of change of B, right? So that is given by small b times density times velocity times area. So velocity times area gives you the flux or the amount of this mass entering and leaving the control volume at what rate it is leaving, right? Because it's also dependent on time. Okay, so I know it might be a slightly confusing or hard to grasp just by these two slides, but as we go along, we will kind of start to gain a better understanding of how this works, right? And the best understanding you'll get is when we actually transition from this chapter to the next one, where we are actually applying this concept of Reynolds transport theorem to mass and momentum conservation. So when you start applying it, so instead of having an arbitrary property B, if you put like for B as equivalent to mass, then you will start seeing how it works out and what makes sense it makes, right? Okay, so as we started off in the previous slide, we are trying to write capital B in terms of small b. So essentially writing the extensive quantity in terms of the intensive quantity, right? So that is small. We kind of introduced or told you how capital B is nothing but small b times mass, and mass is nothing but density times volume, right? So if you are talking about in a general sense, if the density is a variable, you'll have to integrate over the complete volume this density, and if the small b is also variable, right, to get this total b, right? So if it's, let's say, total mass of a quantity or a volume, all right, you will have to integrate the density over the whole entire volume, right, to get the total volume. So that's what this integral essentially represents. So you can rewrite capital B in terms of integral over the control volume of small b times density. Okay, so when it comes to integral of this second term or the flux terms that are there, right? So this is done over the control surface, right? So control surface is nothing but the boundary of this control volume, or the surface that is encompassing this control volume, right? So this is essentially the control surface. It's called as the control surface. Okay, so it gives the net amount. Essentially what it does, this integral essentially gives a net amount of the property of B flowing out of the control volume per unit time, right? So that's essentially what this second term represents, right? So this net flux of property of this extensive property B is given by this expression, or what we found in the previous slide, of B dot out minus B dot in, and that can be given by this integral out here, okay, where V dot n over this area essentially gives you the velocity or the flux of this quantity B, right? So V dot n means just the velocity normal to the surface at any given point. So it's the normal component of the velocity locally at that point. And this will start making more sense as we look at problems in the next section when we actually start applying it, right? Okay, so it's okay if you have not completely grasped it, but try to grasp as much as how much else you can grab, right? Okay, so essentially if you substitute this and this in the previous relationship we called in the previous slide, right, what you end up getting is this relationship here, right? And this relationship is the Reynolds transport theorem. Okay, and so essentially, right, what it's saying is on the left hand side you have a closed system, and if you want to find the time rate of change of this total property B of this closed system or the system approach, right, you can find it or make it equivalent to the open system form of the control volume approach by finding the time rate of change of that quantity B in the control volume plus accounting for how much of B is leaving or entering the control volume. That is the flux part of it, right? Okay, so an alternative expression for this, or a simplified expression actually for this, is where you take the time derivative inside the integral, right? And I will discuss in the next slide of why you can make the simplification, right? Okay, so let's say this basic concept comes back to calculus, right? So if you have a derivative of let's say d dx of a function f and a function g, right? When can you take f out of this function or out of this derivative? What assumption you are making, or what are you saying about f to be able to do this simplification, right? So on what has to happen with f, or what is the uniqueness about f that allows you to take it out of the derivative, right? You can take f out of this derivative only if f is not a function of x, or alternatively if f is a constant, right? So if f is not changing, so let's say instead of this, let's say if I, instead of writing it in terms of random functions, let's say if it was d dx of 3 times x square, right? So f corresponds to 3, which is a constant, and g is x squared, right? In this case, you can take 3 outside and just take the derivative of x squared, right? The reason you can do it because 3 is a constant and it's not changing, right? The same thing is here. Okay, so in the previous relationship you had seen that you had d dt of initially of control volume rho times b dv, right? Okay, so technically this is the derivative, or you're taking the time derivative of not just density and not just b, but also of the control volume itself, right? Because it's inside the time derivative. Okay, so now if you are looking at a fixed control volume, what is the deal with a fixed control volume, right? A fixed control volume is stationary and not deforming, right? So its shape does not change, or its volume does not change, right? So essentially your volume is remaining constant with time because it's a fixed control volume. So similar to this expression, since it's a constant, you can take it out. As a result, you can take the integral out and just look at the derivative of rho times b. Okay, and the simplification will help as you start applying this to different problems, right? So essentially, if you have a fixed control volume, you can take the time derivative inside of the integral, or the other way you can take the integral outside, so you're not worrying about the changes in control volume with time. Okay, so that is kind of a simplification of the Reynolds transport theorem for a fixed control volume. Similarly, you can modify it slightly when you're dealing with a moving control volume, right? Where now, since it's a moving control volume, right, the velocities that you're talking, so essentially your control volume is moving with certain velocity v, right? So let's say if you're talking about this jet impinging on this car, right, and if this car is moving with a certain velocity v car, that means the control volume is moving with that velocity, right? So if we are talking about how much of this jet is impinging or the velocity is entering this control volume, right? In this frame of reference, right, you will be looking at the relative velocity, or you will be concerned with relative velocity. That is the amount or the velocity with which the jet is actually entering the car or the volume of the system, right? Okay, so it is like in some sense talking about, let's say, if you are a biker riding down a hill, right, and if you have a head-on wind coming, right, do you, when you're riding, do you feel more of a resistance to it as you're going if you have a head-on wind? So are you becoming slower if you're going at a slow rate, or you get a higher resistance, right? But if it's a tailwind, right, essentially it is pushing you, so it's in the same direction, right? So you don't get as much of resistance. Instead, you get a boost, right? Okay, so as a result, right, this is where the relative velocity concept comes. So if you are talking about a control volume, right, and the which is moving, so when you're talking about mass entering or velocity of certain property entering or leaving, right, you're not talking with respect to relative velocity, not absolute velocity, right? So relative velocity is just given by this expression VR, right? Is relative velocity is nothing but the fluid velocity at that point locally, right? So that is V jet minus the velocity of the control volume or control surface, which is V car, right? So relative velocity is V jet minus V car, right? So when you're using the Reynolds transport theorem for a moving control volume, you will have to modify the velocities and use relative velocities instead of the absolute velocity, right? So your Reynolds transport theorem for a moving control volume, right, ends up being utilizing VR, right? You need to use relative velocity instead of the absolute velocity. You can make a further simplification since it's a moving control volume, right? Your shape or control volume is not deforming. You can take the time derivative inside, right? We talked about this in the previous one for the fixed control volume, that you can rewrite it as integral of, you can take the time integral outside and then just take the time derivative of rho times b, and the second term remains the same. Sorry, b vr, let me just erase this to remove confusion. b vr dot n dA. Okay, so you can further simplify this Reynolds transport theorem for a moving control volume. Okay, so for a deforming control volume, it goes back to the previous expression that we had, right? The Reynolds transport theorem essentially just becomes dB of this time rate of change of B of the system is equal to the time derivative of this integral or the total property inside the control volume, right? So the key thing you have to be mindful, right? You cannot switch or bring this time derivative inside anymore because your control volume is not fixed, or control volume is constantly changing, right? The shape is changing, right? That's the whole definition of deforming control volume. So you cannot make the simplification of switching up the time derivative. So you cannot take the integral outside the time derivative, because it is also changing with time. So that is the key thing you should be mindful of. So for a deforming control volume, this remains, the time derivative remains outside. Okay, and the rest of it stays the same, right? So your control surface. Second, you account for the flux of this property coming in and out of the control surface. Okay. Now, if you have the most general case of a moving and deforming control volume, right? So your Reynolds transport theorem just becomes dB of the system time rate of change of the system ddt of B of the system is equal to, since it's deforming, it is changing in shape, you cannot take the integral out, so the integral stays in, and then you have rho B dV, and now it's also moving, right? So you will have rho B, your velocity that you'll be using is relative velocity dot n dA. Okay, so this becomes the most general form, right? So these are couple different forms of the Reynolds transport theorem that relates a system approach to a control volume approach for different control volumes, right? So what you would need to at least get out of this is what is the concept you're using, right? And if you know different control volumes, which simplifications you can make for different types of control volumes to the Reynolds transport theorem. Okay, so start to summarize, right? So like I said in the beginning, this will get sink in better as we apply these Reynolds transport concept to mass conservation, which is the next section. So the key takeaways you want to do is when to use which, right? At least have an understanding that in order to connect Lagrangian description to an Eulerian description, you use this material derivative, right? So you use material derivative to connect these two, to find a relationship between Lagrangian and Eulerian description. And this is generally used for doing a differential analysis. If you are doing an integral analysis, right? So essentially you're looking at the global net flux or net mass transfer or net forces acting. Then you're working with trying to connect system analysis to a control volume analysis, in which case you use the Reynolds transport theorem, right? So at least you need to have an understanding of when do you use material derivative, and material derivative is used for differential analysis, and when do you use Reynolds transport theorem. And Reynolds transport theorem is used for integral analysis. And what are these used for? It's used to connect this Eulerian and Lagrangian description and this control volume analysis and system analysis form, right? So finally, if we want to recap what we did, right? So when we are talking about Lagrangian description, right, we talked about how we are following the path of individual fluid particle, right? You're tracking the flow as it goes, right? While in Eulerian description, you do not follow individual particle, rather you look at a flow of fluid parameter at a given location and as it evolves with time. So the second line here is essentially what we just talked about. So if you're looking at the differential analysis, if you want to connect Lagrangian or Eulerian description, you use the material derivative. But if you're doing an integral analysis, in order to connect the system analysis, a closed system with the control volume and open system form, you use the Reynolds transport theorem. Okay, so this top level understanding, at least that is expected that you know that, right? Even if you don't completely grasp the derivation of it. Okay, now the next important thing that you need to have a good handle on is at least understand the difference between a fixed, a moving and deforming control volume, right? So anytime you have this problem, any problem that you're given, depending on what is being asked, right? So it can be the same situation you're looking at, but if you have been asked one quantity, or if your problem is slightly changed, right? So it's giving the example of if you're talking about a moving car versus a parked car, right? That will completely change what kind of type of control volume you're looking at, right? So depending on what is being asked or what is being stated in the problem, you must be able to determine if it's a fixed, moving, and deforming control volume, right? So for that, you just need to ask these two questions in your whichever problem that you have. And which is, the first question is it moving? Is the control volume moving, or is it stationary, right? And the second question is that is it deforming, or that is changing with shape, or is it kind of the volume or the shape does not change at all, right? So that kind of determines if it is one or the other. So if it's not moving and not deforming, it's a fixed control volume, right? But now if it's moving with certain velocity, or if the velocity is changing with time as well, right? It has an acceleration, it's constantly speeding up, right? Right? The velocity is moving, hence the control volume is moving, but it's not deforming anymore, so the shape is not changing, so it's an example of a moving control volume, right? In the case of a deforming control volume, the control volume itself is not moving, right? It's not going places, right? Its boundaries might be changing because that's really relevant to the shape changing. So if the shape is changing, it's a deforming control volume. Now in the most general case, you can have where it can be moving at a certain velocity, but also changing its shape as it is moving along, right? So in that case, the most general form will be a moving and deforming control volume, right? So like we talked about, for a Reynolds transport theorem, for a fixed control volume, right, you can take the time derivative inside because your control volume is fixed, right? So control volume is not changing its shape or volume, right? Hence you can take it out of the time derivative, right? So essentially this first term accounts for the total, how this quantity B is changing inside that control volume with time, right? While this second quantity accounts for, the second term accounts for how much of B is entering that volume from outside or from the boundaries, or leaving the volume from the boundaries, right? Okay, so next up was, if you have a moving control volume, what do you do, right? Since it's moving, we talked about how the velocity locally of the fluid, now that it's moving, your control volume or control surface is moving, what you will be dealing with is relative velocity, right? So like the expression of a head-on wind versus a tailwind, right? So if you have a head-on wind, the amount of air hitting you will be more compared to a tailwind, right? So essentially, when you're talking about relative velocity, you're talking about the fluid velocity locally minus the control surface velocity. Okay, be mindful, here you have vectorial notation, right? So this is subtraction of the vector itself, right? So if, let's say, your object is moving, or control volume is moving with certain velocity this way, and the fluid, so that is your control surface, and the fluid is moving in the same direction, right? Let's say that is Vf. Your relative velocity, what will it be? V fluid, right, minus V control surface, right? Because both are in the same direction, right? Now, if your control surface is moving in this direction, but your fluid is moving in the opposite direction, right? Your relative velocity, or let's say even the magnitude of relative velocity, will be essentially your fluid velocity, which is minus Vf, right, because it's a vectorial notation, and then minus Vcs, right. So essentially, if you're just looking at the magnitude, right, the magnitude of relative velocity in this case is going to be bigger where the velocities of the control surface is opposite to that of fluid than the case where it is in the same direction. Okay, so just be mindful of it. In this expression here, finding the relative velocity is a vector expression, right? So that's the vector lines marked, right? So dash lines on top of a variable. So these dash lines, so if you have a variable with a dash line on top, that means it's a vector quantity and not a scalar quantity. Okay, so lastly, if you're talking about deforming control volume, it's not moving, right? So you don't have relative velocity, you just have the direct absolute velocity of the fluid at the boundaries. But now since the shape can change or is changing with time, you cannot take this integral outside the time derivative, right? So it has to remain inside the time derivative. And lastly, if it's a moving and deforming control volume, this term remains the same, but now over here in the second term about how much of B is entering, or the flux of B entering or leaving the control volume, you have to account for the relative velocity. Okay, so that is kind of the takeaway you need to get from this section, is understand when to use material derivative and when to use Reynolds transport theorem. The most important thing is know or be good at identifying different types of control volume. And then the last thing is how the Reynolds transport can be simplified or gets altered for different types of control volume, right? If you have this understanding, then you're kind of set, and that will help you with the consequent sections where you'll be applying this Reynolds transport theorem, right? And then in the consequent section, when you're actually applying it, this all will start making more sense, because so far we have been treating B as an arbitrary property, so it's still hard to grasp. But once you start applying it, you'll start understanding of how this all works. Okay.